Hey, today we are going to work on long division and synthetic division of polynomials. The first case I'm going to look at is long division of polynomials. The first thing that we're going to do is remember the parts. We have the divisor, which is the part that's going into the larger polynomial. There we go. And then we have the dividend, the number underneath, and what we're after is the quotient, and a lot of times we end up with a remainder. Okay, so if you remember back when we were in grade school, if we divided two numbers like 16 and we divided it by 3, we would get 5 times 3 is 15, and then I would subtract, get 1. Remember that number would have to be less than your 3, and I would stop there and I'll take my remainder as 1, and I can divide that by my divisor, which would be 5 1/3. Um, what we also want to look at is, like, say if we had 3 divided by 18, we would know 6 times 3 is 18. Subtract, we'd have no remainder. And what that meant was 3 times 6 was 18. But these were factors of each other. The quotient and the divisor were factors. And in this first example, 5, which is the quotient, and the divisor 3, those do not multiply together to get back the original 16 because the remainder was 1, not 0. So what we're going to do today is we're going to look at, well, if we use this idea of a 0 remainder, when we deal with higher degreed polynomials, maybe if we could use division, we could break them down to a quadratic, like a third or a fourth degree polynomial that maybe we don't know how to factor or find the zeros of. And we can break it down to a quadratic, which we can handle. So now that's a lot to digest, but it'll make more sense as we do a couple practice problems. So the first thing that you're going to do is you're going to look at your divisor, and you're going to look at the first term, the largest degree, and it is x. And then I'm going to look at the dividend, the number on the polynomial underneath the division bar, and I'm going to look at those two, and I'm going to think about multiplication. Just like I did up in my easy example, I said here's 3 and here's the number 16. What number multiplies by 3 to get me really close to 16? What I'm going to do here is I'm going to say what number multiplies to x to get exactly x squared. So it's not going to be about getting close to, it's going to be exact. And so I know x times x is equal to x squared. And I'm going to put that right above the linear term. And then what I have to do is distribute this x now into both or all of the terms of that divisor's, that polynomial's term. So as a binomial, I already know when I multiply the x and x, I get x squared. That should always match up. And now I have x times 1, which is x. I'm going to draw my bar. Both of these were positive, but I'm going to be subtracting. So when I subtract, I'm going to, with more than one term, I'm going to have to distribute my negative through. So the negative times x squared and the negative times x becomes a negative. So they're always going to switch signs when I subtract. These first terms should always cancel out. I set that up by making them exactly the same and then subtracting them. Then I'm going to combine through addition, now that I distributed the negative, the 3x and the negative x, which gets me 2x. And I'm going to bring down my next term. And I'm going to start all over. So now I'm going to say, what multiplies the x to get to 2x? And I'm going to say, well, that's a positive 2. So they have to be the same and the same sign. So if that was a negative 2x, I would be multiplying by a negative 2. But it's a positive. So I have 2x times x is 2x. And I have to distribute this 2 also to both of these. It's the same thing every time. And then 2 times 1 is 2. Now I'm going to distribute my negative in. Both of these were positive, so they switch to negatives. I'm going to add down, these cancel, and I get 3. Notice there's no more combinations of what can multiply by x to get 3. That's not possible. Now you know you're at your remainder. Okay, so this one didn't evenly divide. And so when I write my remainder, you'll typically see it as 3 over the divisor of x plus 1. And this would be my final answer. And notice, if I tried to factor this, there are no factors of 5 that add to get me 3. So there's not going to be 2 zero remainder factors here. It's not factorable. And so that kind of shows that x plus 1 is not going to be a factor of x squared plus 3x plus 5. Okay, so my next one is I have a 4-term cubic in the dividend, and I have a first-degree polynomial in the divisor. So I always want my smaller degreed out front and my bigger degreed polynomial underneath, just like when we divide the other way, we want the larger number underneath. And I'm going to multiply. So same thing. So I'm going to look at these leading highest degreed terms. I'm going to say what multiplies by x to get exactly 6x cubed. So I know I need a 6 and an x squared. And that gives me 6x cubed. But don't forget, I got to multiply the 6x squared also to that -2, the second term in the binomial. I get negative 12x squared. Then I'm going to distribute my negative through. I'm subtracting. With a binomial, you have to distribute to both terms, not just the first one. My leading terms right here should cancel out. And then I'm going to combine, get negative 7x squared. And I'm going to bring down my 16x. Some people like to bring down the -4. That's just up to you. Okay, and then I'm going to multiply again. So what multiplies x to get negative 7x squared, which would be a negative 7x. So remember, it's got to be the same sign. Now I'm going to multiply my negative 7x to my -2, and I get a plus 14x. Now I'm going to be subtracting, so I've got to change the sign. And these leading terms will always cancel out because that's my goal on every time, is to make them the same term, same sign. So when I subtract, they cancel out. And then 16x minus 14x is 2x. And I'm going to bring down the -4. Again, I'm going to say what multiplies by this x to get 2x, and that would be a plus 2. And I get a 2x multiplied to the -2, and I get -4. Distribute these both in, and they both cancel out, giving me a remainder of 0. So now I know that x minus 2 is a factor of 6x cubed minus 19x squared plus 16x minus 4. So when I get a 0 remainder, I can write my polynomial like this. Oops. Just like I did up here when I found my 0 remainder, right? So I know 18 is divisible by 3, and 6 times 3 is 18 with a 0 remainder. So then I can say that 6 and 3 multiply exactly to get 18. Just like here, I can say, because I had a 0 remainder, x minus 2 times the quotient, my answer that I got, 6x squared minus 7x plus 2, those multiply back to get what I initially divided into the dividend, which was 6x cubed minus 19x squared plus 16x minus 4. Okay, so why would we want to do this? Because now, if we looked at our very first polynomial, the big polynomial underneath in the dividend, we probably would not be able to factor that. Okay, so not factorable. We'd need a calculator to find all the zeros. However, because I could find a divisor, I broke my cubic that I couldn't factor down into a linear, this x minus 2, and this quadratic. Now I should be able to go further. Like if I wanted to find the zeros of this quadratic, I could either try factoring it or I could use the quadratic formula. But either way, I could get all three roots. Okay, so that's what we're going to look at here. We want to look as x plus 4 a factor of each polynomial? If so, write in factored form. So I'm going to take x plus 4 and I'm going to divide it into x squared plus 6x plus 8. And again, I'm going to say x. Want it to make it multiply to get x squared, so I know that's an x. I'm putting it above my linear term of 6x, and I get x squared multiplied to the second term, 4x. Those are both positive terms, so when I distribute my subtraction sign in, they both become negative. I'm going to add down the next one. And we just keep repeating. So I'm going to do the same thing. What multiplies by that same x, that's not changing, to get 2x, and that would be plus 2. I get 2x plus 8. Change my signs to the subtraction, and I get a remainder of 0. So now I know x plus 4, this what I was dividing by, times x plus 2, are going to multiply back together to get x plus 6x plus 8, which we could have factored that on our own. But sometimes looking at an easy problem that we already know factors and showing it through division is a lot easier to maybe wrap the brain around what we're doing. Because definitely on that one, we wouldn't divide, we would just factor. But what if we came into a problem like number 2, and we couldn't factor it, but we wanted to find all the zeros or x-intercepts solutions? If I divide by this function by x plus 4 and their remainder, then I break this cubic 1 degree less to a quadratic. So x squared times x is x cubed, and then times 4 is 4x squared. Those are both positive terms, so when I distribute my subtraction sign through, it changes them to negative, down, bring down. Okay, now I want to multiply x to get negative x squared, which would be a negative x. Take that negative x, multiply it by my 4, get 4x. Change my signs because I'm going to be subtracting, and that is going to cancel there. Get negative 2x, bring down my negative 7. And now I'm going to find what multiplies by x to get negative 2x, which is a negative 2. Get negative 2x minus 8. Bring my subtraction sign through. I get a remainder of 1. This one close, but not a factor. So I can't say x plus 4 times x squared minus x minus 2 multiplies to get back the larger cubic polynomial. Okay, example 3 and 4 are ones that when things aren't perfectly written for us, how are we going to handle that? So here I have x minus cubed, my smaller degree polynomial, and I'm dividing into this cubic, but notice there's some terms missing. I'm missing my quadratic, I'm missing my linear, some room, and my constant. You need to place 0 placeholders when you're missing a term, otherwise it's really hard to kind of keep track of all your terms. So I'm going to do the same thing. X times what equals x cubed, and that's x squared. And I get x cubed, and then I get a minus 3x squared. So notice that 0 up there is just a placeholder because when I multiply, I'm going to generate these degree terms, the quadratic and linear. And if I don't have the zeros up there, I'm going to put them with the 27, and it's just really hard to follow your work and keep organized. So now I'm going to distribute a negative through for my subtraction. And I'm even going to bring down that 0x. Okay, so what multiplies by x to get 3x squared? That would be plus 3x. Gives me a 3x squared. When I multiply it by the negative 3, I get negative 9x. I'm subtracting, so I'll distribute that subtraction sign through. And then I'm going to bring down my negative 27. Okay, lastly, what multiplies by x to get 9x? That would be a positive 9. 9 times 3 is negative 27. These match up perfect, so when I distribute my negative, they're going to be opposite signs, giving me a remainder of 0. So what this means is I have x cubed minus 3 plus 3x plus 9. And if you remember difference of cubes, remember square, multiply, 3 and x gives me 3x, and then squared, 3 squared is 9, same, opposite, always positive. Notice how I did my long division got me back the difference of squares. And I know that this is imaginary, so if I wanted to find these solutions, I would have this quadratic formula. Okay, last example is I'm going to take my smaller polynomial degree, this is a quadratic, and I'm going to divide it into my cubic. So first thing to notice is I started to write this wrong, right? Because my fourth power needs to come first. I said third degree. I almost got tricked by the problem myself. And I need to make sure that I go in standard form from highest degree to smallest. Notice I don't have a quadratic, so I'm going to add a 0. I do have a linear and a constant. Okay. So just to let you know, when you divide two polynomials together, if you look at their 2 degrees, this is a quadratic and it's going into a fourth. And when I divide those, what you're going to be left with is the subtraction of those degrees. So have a fourth degree divided by a second degree, I'm going to be left with a second degree polynomial above. If this, if I was like before dividing this outside, my divisor, and it was linear, and it was a first degree, then I would be outputting a third degree polynomial. Okay, so same thing, doesn't matter. I have an x squared and an x to the fourth. We do the same thing. So I get an x squared. So notice I'm going to produce a quadratic when I divide these, just like I said. And then I have to distribute now to all 3. So I have x to the fourth. I have an x squared times a negative x, which is a negative x cubed. And I have an x squared times a negative 3, which is a negative 3x squared. I will be subtracting this bottom polynomial, so I need to distribute my negative through. And cancel, bind, bring down. Again, I'm going to start and do the same thing. What multiplies by x squared to get 6x cubed? That would be a 6x. And I'm going to get 6x cubed. And now I've got to multiply that to the negative x, and I get negative 6x squared. And then negative 18x. And I'm going to be subtracting, so I'm going to distribute my negative through, cancel, combine, and this should be my last time. I say what multiplies by x squared to get 9x squared, that would be plus 9. I know I get a 9x squared, and then I get a minus 9x, and then I get a negative 27. Switch, cancel, combine, and then I'm going to combine here, and this is my remainder. And if I wanted to write my remainder over my divisor, so these are not factors of each other. So we'll practice a little bit of long division. As you can tell, it's really just practicing and getting a knack at going through the motions of what multiplies, change your signs, add down, and get to the remainder. It's important that you practice this so that we can use it to graph a larger powered polynomial, which we'll be doing later in the chapter.